This lesson deals with Supplemental Problem 212. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 25. The first Texas Instruments Pocket Scientific Calculator that had trig and log functions on it was a model SR50. In fact, this was a calculator that I purchased when I was in college. I took it apart, which was a great leap of faith at the time, because the cost of this calculator was like buying a used car. And what I found inside was an incredibly simple charging circuit. The batteries were nickel-cadmium, or we just called NiCad, and they were commonly used in rechargeable drills and things of that nature at the time. And just a diode, a 1 in 4001 diode. This is hooked up to what's called a wall wart, and this is a transformer plugged into the wall. And the secondary of the transformer, I measured the voltage. It was around 5 volts as a sine wave at 60 hertz, and there was some winding resistance, about 10 ohms. I took some measurements on this, and when the batteries were fully discharged, they were sitting at about a volt. So about 3 volts total here. And when they were fully charged, the voltage of each battery was about 1.3 volts. First, let's sketch the charging current versus time for the discharged and charged states of the calculator, and let's label the peak currents. It'd be kind of nice if this was an LED and we could use that as an indicator to indicate whether we're fully charged or not. We're going to put an LED in here and redesign this circuit. Let's put a piecewise linear model for the diode. That consists of an ideal diode and a VD-on. In Supplemental Problem 2.5, we had some data points for a 1 in 4001 diode, and I'm going to pick the larger current value for the voltage. That's because this was taken at about 100 milliamps with a voltage about 0.8 across the diode, and that's probably the neighborhood of the charging current in this circuit. Then I have 3 batteries. I'm going to take from one voltage level to another. And then I have a wall wart that's a 5 volt sine wave with a 10 ohm series resistance due to the windings. So we could sketch V sub S versus time. It's going to go up to 5 volts and then down to 5 volts. Its period is 1 over 60, and that's 16.7 milliseconds. The input's going to have to increase and get to a point where it can get current to flow because I've got a couple batteries here in series with the voltage source V sub S. So let's find the transition point. At the transition point, there's no voltage across the diode and no current through it. The voltage V sub S would be the rise in voltage would equal the drop of 0 times 10 plus 0 across this diode plus 0.8 plus V bat 3 times. That's this equation right here. That's equal to 0.8 plus 3 times V bat. And V bat's going to vary between 1 volt and 1.3 volts. We mark that point on the curve. When we're below this voltage, no current's going to flow, and when we're above it, current's going to flow, and then it'll come back and shut off again. The charging current is also the current in the 10 ohm resistor, so let's find the voltage across here and divide it by 10. This node voltage at the maximum of the input is 5 volts, and then this node voltage, when current's beginning to flow, is going to be 0 plus 0.8 plus V bat 3 times. 5 volts minus that drop divided by 10 would be the charging current maximum value. Let's figure out what it is for the different values of the batteries. If the batteries were discharged down to 1 volt, then this becomes 1 volt times 3, or 3 volts, and that turned out to be 120 milliamps when it's fully discharged. And as we approach full charge, this battery voltage approaches 1.3 volts, and of course 3 times that is 3.9. That takes us to 30 milliamps. So we have a very large charging current, and eventually drops off to a trickle charge. See if we could add an LED in place of the diode so that we'd have a visual indicator when we're charging and when we're basically fully charged. I'll use a red LED, and in Supplemental Problem 210 we said that was about 1.8 volts. This is 1 volt higher than the diode we had. I need to increase the voltage source V sub S by 1 volt to keep the same current levels. Make this a 6 volt wall wart, and then if you solve for the current like we did above, it's going to be 6 minus the quantity now, 1.8 plus 3, and 1.8 plus 3.9. So we get the same currents again. And here's my final design. Should make one note here. The voltage across this LED maximum, when it's off, is going to be this node voltage, which is going to be minus 6, and then this would be minus 3.9. We would have 9.9 volts across this LED. I looked in data sheets of LEDs, and I didn't see a breakdown voltage. They gave a reverse voltage and a current level. I had to measure a red LED and see where it breaks down. It's around 30 volts. And this is Supplemental Problem 212.